All right, let's talk a bit about diffraction and diffraction gratings and how we actually do the calculations for these. So basically, if you're not so familiar with how we derive the equations, then you might have a bit of trouble when it comes on to solving questions like this, right? So the first thing that I really need you to get is simply that if, for example, the wavelength, lambda, is greater than the gap width, then diffraction will increase. But if the lambda or wavelength is less than the gap width, then diffraction decreases, right? And diffraction refers to the spreading out of waves. So let's say you have a point source, and usually the point source used is a laser, because laser light has waves which are coherent, right? Meaning that they're always in phase, and also it's of a single wavelength, right? So when say the laser light actually starts the process and you have the light source going towards, or the waves going towards the slits, then what you're going to find happening is these these waves will go through the slits and they'll start to spread out and they'll form something looking like this, right? But because there are two slits, you're going to have that happening twice. So the waves will overlap and you'll see this, right? So these here represent peaks and troughs of a wave, right? So this is either a peak or it's a trough. So, on a regular wave, the peaks are the highest points, right? While the troughs are your lowest points. So that's essentially what we're looking at right here. So every time you have an overlap like this, where you have the peak or a trough and a trough overlapping, then that's going to be constructive interference. So they're going to amplify each other. So once say the light is projected on a screen, you're going to have something looking like this being formed, where this would be maybe, not maybe, but really, or central bright fringe. So you'll see an alternation between bright and dark, bright and dark, bright and dark. But as you go out towards the end, the bright marks will get actually lighter, right? So this is where we'd say you'd have a 0th order fringe, which represents zero phase difference, to be honest. And here you'd have one wavelength and then two wavelengths. If you want to do this, it's -1 or -2 lambdas, just going down like this. Now, what does this have to do with anything? It's probably what you're wondering. So if we have, say, the light source traveling from this point and this point right here, and creating a central bright fringe right here, then I hope you can see this, but there wasn't much travel, right? The line from here to here is the same length. So let's call that x1. The line from here to here is the same length. So we'll call that x2. So right now, if we're supposed to take x2 and x1 and find the path difference, delta x would be equal to 0. And by a general rule, the path difference are multiples of the wavelength. So this is 0. If we go to another bright fringe, maybe up here, then it would be 1 lambda. Up here would be 2 lambda, and so on, right? And it depends on the path difference, as I said. Now, continuing to observe a few things. If we measure from here to here, this would be the distance between the two slits from this point over here all the way to this side. That's the distance the slits are from the screen, right? And let's take into consideration, let's change the color here to here maybe. We'll call this Y, which is the distance between the central fringe and the first order bright fringe. So we say that's first order. 2 lambda would be second order bright fringe, right? So just like that. So Y represents the distance between the first order and the central bright fringe. And we can even extend this a bit more. 2Y would be the distance between the second order and the central bright fringe. And if we happen to extend this line and maybe add 3 lambda, then 3Y would represent the distance between the central bright fringe and the third order bright fringe. Okay, let me add another line and perhaps clean this up a bit so we don't get confused. All right. Now, remember I told you we'll need this, the 0th order, and maybe put that as the first order bright fringe. So the distance between that we'll call Y. The distance from here to here, here to here, yeah? That's the distance from the split to the screen, right? We'll call that large D. And boom, that's a right angle. Now, if we take a look at this triangle right here, we'll realize, right? We will realize that it's a right angle triangle. I can take it out. Where D is right here, this is Y, and we have an angle right here, theta, which would actually be equal to the angle right here because these are Z angles or alternate angles, right? So we can pick up what this is. So from that, we can derive an equation. If this is the hypotenuse, this Y would be the opposite side, and here D would be the adjacent side. So I hope you can recall SOHCAHTOA, right? We are given the opposite side and the adjacent side. So we can use the tan ratio, where tan theta is equal to the opposite side divided by the adjacent side, which means tan theta, therefore, is equal to Y over D, meaning the distance between the central fringe and whichever order fringe you want, and the divided by the distance between the slit and the screen. Now, because these angles are extremely small, because the slits are actually very close together, the sine of any angle, that small angle, relatively small angle, is equal to the angle itself. And similarly for tan theta of any small angle is equal to the angle itself as well. You can use 0 to test this. Small numbers are relatively close to 0. So sine 0 is actually equal to 0. And similarly, tan 0 is equal to 0. So we can actually write tan theta as sine theta. And that's equal to Y over D. And we'll need this a bit later. So keep it in mind. So this is the first equation that we are going to pay attention to. The next would be in a case where, remember, this point was our central fringe, right? Or 0th order bright fringe. Now, let's say this is our first order bright fringe. There is now a path difference. This is x1, this is x2. But x2 is a bit longer than x1. So let's say we made a cut about right here. Let's say, boom. No, maybe these now will be relatively the same distance, x1 and x2. So this portion at the end right here would represent the path difference, delta x, all right? And apart from that, let's say we made a right angle right here. I'll pull out this triangle very soon. And what else can we identify? We'll know theta right here because theta here will be equal to the angle theta right here, right? So if I pull this out, this is a right angle, right? And kind of shape this triangle a bit. Let's put that there. We know that theta is here. We know that this is delta x, right? And we also know that from here to here is the distance between the slits. Let's make that a bit cleaner. So from there to there, that's the distance between the slits. So if this is the right angle, then this is the hypotenuse. Maybe I could have done a better job at drawing that. Let's say that's 90 degrees or no. All right, let's work with what we have so far. So this would be the hypotenuse. This side would be the opposite side. And so what do we have? Opposite side and hypotenuse. So ka, toa. Opposite and hypotenuse, that's sine. So sine theta is equal to the opposite side, which is the path difference, divided by the hypotenuse, which is the distance between the slits. If we rearrange this and make path difference the subject, the path difference would be equal to sine theta multiplied by the distance between the slits. Now, another thing is, I told you earlier, or I mentioned it, that the path difference usually multiples of lambda, right? So that means that lambda multiplied by an integer n is also equal to the path difference. So that's how we got 1 lambda, 2 lambda, 3 lambda to represent the orders, right? So we can further substitute delta x for that in our equation. So lambda times n is also equal to sine theta multiplied by d. Now, I'm just going ahead and substituting, because you can use the first equation on its own. You can use this substituted equation, and I'm going to further substitute sine theta that we got earlier to create a new equation, right? So depending on what is given in the questions, you'll have to pick up, which one of the formulas you'll use, right? So remember earlier I said sine theta is equal to the distance between the fringes divided by the distance between the splits and the screen, right? So if I substitute sine theta into this, we'll get lambda n is equal to y over capital D multiplied by common D being the distance between the slits, capital D is the distance from the slits to the screen. So this is another equation. Lambda n is equal to yd over d. All right, so let's just look at a sample problem very, very quickly. So we have light of a wavelength 600 nanometers. So lambda equals 600 nanometers. From a single source passes through two slits, which are 0.1 millimeters apart. So D is 0.1 millimeters. An interference pattern is seen on a screen 1.10 meters from the slit. How far is the second order bright fringe on the screen from the central fringe? So we're looking for Y, right? By outlining these, you can easily pick up which formula to use, right? So we started out with, we had sine theta is equal to Y over D. Issue though, we don't have theta. So we'll need to substitute sine theta for something. We have lambda though, and we have small d, right? So that means that maybe we can use this. Let's look at the other equation that we had. We had this. Lambda times n is equal to sine theta times common d. Not bad, right? So let's put sine theta or substitute y over d for sine theta. So lambda times n is equal to yd over d. Great. N would be 2 because it's a second order, the second order bright fringe that we're asked about, right? So lambda being 600 nanometers, need to convert that to meters so that we can ensure that our answer is in SI units. So 600 times 10 to the minus 9 meters, right? Minus 9 meters times n, which is 2. We're solving for y. And if y is the subject, y would be equal to lambda n times capital D, right? All over common D. So the distance between the split on the screen is 1.10 meters. And divide that by 0.1 millimeters, but we need to put that in meters as well, which would be 0.0001 meters. 0.001 meters. Meter will cancel a meter. So that would mean that y, meaning the distance between the central fringe and the second order bright fringe, would be equal to whatever result you'd get when you put this into your calculator. So put it in. And I got 0.0132 meters. So that's how you calculate diffraction grating.